Salam, peace be upon you. Sometimes we say next, as if it is obvious, but it is not. In this part, we learn a strict rule. We do not say next unless we can prove what kind of next it is. We build 5 safe kinds of nextness, like 5 safe bridges, and each bridge needs a stamped ticket. If we cannot prove the bridge, we do not walk it. We say, adjacency is undefined. That is how change stays real and never turns into a story. Recap, told simply, with everyday examples. Let's remember where we are, in the simplest way, using scenes we all know. Imagine we are holding a phone and we take a photo of a room. In the photo, there is a chair by the window. Now we take a second photo later and the chair is near the door. Most people would instantly say, the chair moved through time. But we decided to be stricter than most people. We said, we will not use time as a magic river. We will only use what we can prove in public. So in part 1, we learned the first big rule. Change is not a feeling and not a story. Change is a certified relation between 2 certified states. A certified state is not a guess. It is a folder we can show to others. In part 2, we face the hardest confusion. If we do not start with time, how can there be change? And we answered with one sentence, spoken clearly. Public change of S1 and S2, if and only if there exists an update certificate from S1 to S2 with all gates passing. Then we learn to refuse fake change. For example, someone tells a story but cannot show any documents. That is narrative-only change. Someone changes labels and calls it change. That is gauge-only change. Someone cuts the picture differently and calls it change. That is cut-dependent change. Someone sees noise and calls it motion. That is uncertainty masquerade. Someone jumps from tiny to big without permission. That is scale smuggling. Someone says, I feel it changed, but cannot show public evidence. That is observer projection. In part 3, we noticed a new danger. Even if we demand certificates, we could still cheat by inventing new words. So we froze the language. We said, physics does not get new words just because it is convenient. We made a fixed runtime alphabet: state package, adjacency proof, transformer, update certificate, and ledgers. If a claim uses a forbidden word, we refuse it. In part 4, we built the most important object so far, state package S of W. We said, a state is not what you imagine is there. A state is what survives a public compiler. If it cannot be hashed and replayed, it is not public. We used everyday examples: a hospital file, a camera record, a recipe card. They are not the thing itself, but they are the public folder about the thing with instruments, boundaries, and uncertainty. And we said, without sealed state folders, change becomes poetry again. So now we have 2 strong things. 1, we can create sealed public states. 2, we can say change only if there is an update certificate. Now we reach the next problem that quietly destroys many theories. Even if we have states, how do we decide what counts as next? Because people say next too easily. They say next moment, next step, then it happened. But next is a dangerous word. If we use it carelessly, we smuggle time, distance, and hidden assumptions. So part 5 installs a new discipline, adjacency classes. Type nextness without time. And we will do it with very simple everyday bridges. Opening rhythm, the hook. Imagine we are standing at a train station. A train is on the platform. Then the train is gone. Someone says, the train moved. But another person asks, from which platform to which platform? Which track? Which timetable? Which camera? Which ticket scan? Because if we do not know what the next means, we do not know what happened. Pause. Now we say the bridge line clearly. Episode 14 gave us the alphabet of certified structure. Episode 15 gives us the grammar of lawful change. Episode 14 compiled what is publicly readable inside Windows. Episode 15 certifies how one compiled page can legally lead to another. And the question for today? Today we are asking, when we say next, what do we really mean? Part 5. Adjacency classes. Typed nexts without time. We begin with the rule we will repeat many times. We do not say next unless we can prove the adjacency type. If adjacency is undefined, the honest answer is undefined. Chains are not narratives. Chains are validated compositions. Now we translate that to a simple picture. Imagine 5 different ways 2 pages in a notebook can be connected. Sometimes they touch because they share the same story. Sometimes one page is a zoomed-in version of another. Sometimes one page is the same thing, but at a bigger scale. Sometimes one page is the same thing, but moved across the room. Sometimes one page is the same thing, but at the boundary where rules change. These are different kinds of connection. If you mix them, you lie without meaning to. So we build 5 types of adjacency. We will not use shortcodes in the narration. We will use human names, but we will still keep the meaning exact. The 5 adjacency types. 1. Overlap adjacency. 2. Refinement adjacency. 3. Scale adjacency. 4. Transport adjacency. 5. Boundary adjacency. Each one is a legal bridge between 2 state folders, and each bridge needs a proof object. We call that proof, an adjacency proof. If we cannot produce an adjacency proof, we say adjacency is undefined. That sentence is honesty. Now we build them one by one, using everyday scenes. Scene 1. Overlap adjacency. 2 windows share the same piece of reality. Imagine we are in a city. 2 cameras are watching the same street corner. Camera 1 sees the whole street. Camera 2 sees only the door of one shop. There is a small area that both cameras see. That shared area is the overlap. Now we compile 2 state folders. State package S of W1 for camera 1's window, state package S of W2 for camera 2's window. Now we ask, can we say these 2 windows are next, in the sense that they touch the same world? Only if they have a certified overlap. Only if their passports match enough to compare. Only if their invariants agree within uncertainty. Here, the illusion people fall into is simple. They say, both cameras are in the same city, so they must match. But that is not a proof. One camera might be blurry. One camera might have wrong time settings. One camera might be shifted slightly. So we refuse the illusion. We do not say next. We prove overlap adjacency. Now we translate it into the Holophase runtime language, in spoken form. To claim overlap adjacency, we must show the 2 domains, D of W1 and D of W2, have a certified overlap region. The passports, pi of W1 and pi of W2, allow comparison. The invariant basis, I of W1 and I of W2, agrees on the overlap within U of W1 and U of W2. If that passes, we produce an adjacency proof. If not, we produce a refusal. Now we walk through Gate 2 in a lived way. Gate 2 is the adjacency legality gate. It is like a security guard at a bridge. It asks, do you have a ticket for this bridge type? If we cannot show overlap evidence, Gate 2 stops us. Now we do the intervention split moment in this scene. Imagine the shopkeeper changes the light above the door. Camera 2 suddenly sees a brighter door. Camera 1 does not. Did the street change, or did the camera window change? We check the passports. If the exposure settings changed, that is a window change. The passport records it. We refuse to call it world change. Now we add a stress test. Stress test. Phi goes to phi plus C. Spoken. Phi goes to phi plus C. Translation. If we rename the street signs, did the buildings move? Answer. No. So the overlap decision must not depend on labels. It must depend on invariants. If the overlap claim changes when we just relabel, it fails Gate 4, invariant safety. Now we give a simple prediction. Prediction. If two cameras truly overlap and their passports are compatible, then any invariant measured on the overlap must match within uncertainty. If it does not, the overlap adjacency claim is refused. Now we move on, because we need at least 3 different scenes in this part. Scene 2, refinement adjacency. Same place, but one window is more detailed. Imagine we are reading a map. One map shows the whole city. Another map shows only one neighborhood, but with street names, small alleys, and house numbers. The neighborhood map is not a different world. It is a refinement. It is the same world described with more detail. That is refinement adjacency. The illusion people make here is subtle. They assume that more detail is always better and always compatible. But it may not be. The detailed map might be outdated, or it might use a different coordinate style, or it might be missing some streets. So we refuse the illusion. We do not say, this is just more detail, trust me. We certify refinement adjacency. Now we translate. We have 2 windows, W1, wide window, lower detail. W2, narrow window, higher detail. Refinement adjacency means W2's domain sits inside W1's domain in a certified way. W2's passport is compatible with W1's passport, and the shared invariants agree where they overlap. But there is also a special rule. Refinement must respect ceilings. Ceiling is spoken as nmax of W. So we say, if nmax of W1 is low and nmax of W2 is high, that is allowed only if we do not pretend the low detail window had the higher detail. We are not allowed to upgrade the coarse window by imagination. We can refine, but we must keep honesty. Now we speak it in a very simple analogy. If one person tasted soup and said, it is salty, another person used a spoon and measured salt exactly. The second is more detailed, but the first did not become detailed. The first remains coarse. Refinement is a relationship between 2 different public descriptions, not a magical upgrade. Now we connect it to Gate 2 and Gate 8. Gate 2 asks, do you have the proof of refinement? Gate 8 asks, did you smuggle time or metric while pretending to refine? For example, if someone says, refinement is the future state, that smuggles time. Refinement is not future. Refinement is a relation between descriptions. Now we give a prediction. Prediction. If W2 is a true refinement of W1, then when we project W2 down to the level of W1, the shared invariants must match within uncertainty. If not, refinement adjacency is refused. Now we continue. Scene 3. Scale adjacency. Same thing, but micro and macro must be linked honestly. Imagine we are watching a crowd from a rooftop. We see a group moving like a wave. Now we go down to the street. We see individual people walking. The rooftop view is macro. The street view is micro. People often jump between them and say things like, the crowd decided, the crowd flowed. But how do we connect micro and macro without cheating? That is the problem of scale adjacency. The illusion here is big. People think scale change is free. They think you can jump from atoms to weather with one sentence. But that is smuggling. So in Holophase, scale adjacency is only allowed if we have a declared bridge. We call it a coarse-graining interface later in the episode, but in this part, we already installed the discipline. Scale adjacency requires declared interface. If the interface is not declared, adjacency is undefined. Now we translate in simple terms. Scale adjacency means we have two state packages. One is a fine description, one is a coarse description. We are allowed to connect them only if we can explain publicly what information we threw away to go from fine to coarse. If you cannot say what you threw away, you did not scale change. You hallucinated. So we speak the rule slowly. Scale adjacency is legal only if a declared coarse-grain interface exists. Now we connect it to gate 2 and gate 8 again. Gate 2 asks, do you have the interface proof? Gate 8 asks, did you smuggle the macro as a new primitive thing? Because macro is not a new substance. Macro is a declared loss of detail. Now we give a simple example. Imagine we count money. Micro, every coin and every note. Macro, I have about 50 pounds. The macro statement discards details. It is useful, but it is not free. If you say you have 50 pounds, you cannot later claim you have the exact same coins. That is the cost of scale. So scale adjacency records what is discarded. Now a prediction. Prediction. If we claim a macro state is scale adjacent to a microstate, then applying the declared interface to the microstate must produce the macro state within uncertainty. If it does not, scale adjacency is refused. Now we do a small recap hook. We are still answering one question. What is change? And now we learned change needs nextness. But nextness is not one thing. It has types. And each type needs proof. Now we continue with the last two adjacency types. Scene 4. Transport adjacency. Same pattern, moved across a place without assuming distance as a primitive. Imagine we are at a market. A fruit seller has apples. In the morning, the apples are on the left table. Later, the apples are on the right table. People say, the apples moved. But we are strict. We do not start with distance as a magic primitive. We start with certified relations. So transport adjacency is the legal bridge that says, this state package and that state package are connected by a declared transport mapping. In very simple language, we need a rule that tells us how to match left table apples with right table apples. We cannot just point and guess. Now we translate. Transport adjacency requires two windows with compatible passports. Domain typing that allows us to compare. A declared transport map, which we can call psi if we want, but we will say transport map for narration. Invariants that remain stable under the mapping within uncertainty. If we do not have the mapping, we do not say moved. We say adjacency is undefined. This is how we avoid smuggling motion as a primitive substance. Remember the tri-unity rule. Time, space, and motion are readouts from certified structure. They are not primitive substances. So transport adjacency is how motion will later be read out, not assumed. Now we do a stress test here again. If we change labels, does the transport claim change? No. If it does, it fails invariant safety. Now we give a prediction. Prediction. If a transport mapping is correct, then invariants transported from the first state package to the second must match within uncertainty. If not, transport adjacency is refused. Scene 5. Boundary adjacency. Nextness across a border where rules change. Imagine a school. Inside the classroom, the rules are quiet voice, raised hands. Outside, in the playground, the rules are different. Now imagine we are describing the same child. Inside the class, the child is sitting. Outside, the child is running. The border matters. If we do not record the border, we confuse rule systems. That is boundary adjacency. The illusion people make here is they forget boundaries. They speak as if rules are the same everywhere. But real life is full of boundaries. Borders, membranes, doors, fences, cut regions. Holophase is very careful about boundaries. So boundary adjacency is the legal bridge for nextness across a typed boundary. Now we translate. Boundary adjacency requires a domain D of W that includes colors and typed boundaries. Proof that we are allowed to compare across that boundary. Passports that include how the boundary was handled. Stable invariants or control changes across the boundary within uncertainty. If boundary typing is missing, adjacency is undefined. Now we give a prediction. Prediction. If boundary adjacency is legal, then the boundary behavior must be consistent across repeated audits under compatible passports. If it changes when the boundary handling changes, we classify it as boundary typing failure or passport mismatch. The adjacency registry. The place where all these bridges are stored and checked. Now we step back and explain the main tool of this part. We build an adjacency registry. In everyday language, it is like a rule book of bridges. Each bridge type has what ticket is needed, what evidence is needed, what failure looks like, what proof object is produced. When a claim tries to say next, it must point to this registry. It must not improvise. And each adjacency proof is stored in a proof ledger, so later strangers can audit. Now we explain adjacency chains. People love chains. They say, first this, then this, then this. But chains can be fake stories, so we install chain validation. A chain is legal only if each step is legal and typed, and the composition rules allow it. For example, overlap adjacency followed by transport adjacency might be allowed, but only with proofs. Refinement adjacency followed by scale adjacency might be allowed only if the interface is declared. If the chain type is not validated, we refuse it. Now we emphasize the refusal sentence again, because it is a powerful anchor. If adjacency is undefined, the honest answer is undefined. This sentence is the opposite of mythology. The one pipeline line spoken as one sentence. Now we speak the required toolchain line as one clean spoken sentence. 5.0 certified windows and passports lead to building state package S of W. Then we prove typed adjacency. Then we choose a legal transformer. Then we run the 8 update gates. Then we produce an update certificate or a refusal certificate. Then we write to ledgers with uncertainty lineage. Then we run invariance stress tests. Then we issue predictions and failure signatures. And if broken, we revoke and archive. That line is the whole machine. Part 5 installs the proof typed adjacency section. Without it, the machine cannot move. because it would not know what next means. Predictions, delivered like receipts. Prediction 1. If we claim any nextness, we must be able to name the adjacency type and produce an adjacency proof. Or we must say adjacency is undefined. Prediction 2. If two windows claim overlap adjacency, then their shared invariants must match within uncertainty on the overlap region under compatible passports. If not, adjacency is refused. Prediction 3. If a claim uses next but cannot specify whether it is overlap, refinement, scale, transport, or boundary, then gate 2 fails and the claim must be refused as undefined adjacency. Prediction 4. If a claim uses a hidden time parameter to connect two states, gate 8 detects primitive smuggling and refuses the adjacency. Failure signature taxonomy for this part. If the adjacency claim fails, we classify the failure, not excuse it. Passport mismatch. Pi of W1 and pi of W2 are not compatible. Domain illegality. D of W is not typed correctly or boundaries are wrong. Invariance failure. The claim changes under phi goes to phi plus c, or under cut relocation, or under lift shift by 2 pi integers. Scale smuggling. Micro to macro claim without a declared interface. Transport map missing. Movement claimed without a declared mapping. Uncertainty underpriced. Differences are within noise but sold as change, or noise is ignored. Defect instability mismatch. Topology tokens do not match where they must. And if the claim keeps failing in a way that cannot be fixed by honesty, it may become an escape candidate later. But not yet. First, we try to compile cleanly. Falsifier for part 5. Falsifier. If there exists a publicly repeatable situation where two state packages are clearly connected in a way that everyone can audit, but no finite set of typed adjacency classes and proofs can represent that connection without secretly importing time, distance, or other forbidden primitives, then the adjacency system is incomplete and must be revised. In plain language, if nextness cannot be made public without cheating, this part is wrong. Ending. What goes in the ledger and what revokes this part. Audit artifact. What goes into the ledger? We store the adjacency registry itself with 5 adjacency classes: overlap adjacency, refinement adjacency, scale adjacency, transport adjacency, and boundary adjacency, each with clear validator rules and required evidence. We store the format of an adjacency proof object, including what it must cite. Passport identifiers pi of W, domain typing D of W, invariant comparisons within U of W, and any declared mapping or interface identifiers. We store chain validation rules, meaning how adjacency proofs can be composed and when composition is forbidden. We store smuggling detection reports that flag illegal uses of time as a variable, simultaneity assumptions, metric leakage, and scale leakage. We store proof hashes and chain validation logs so strangers can replay the adjacency decisions. Revocation clause. If any certificate uses the word next without producing a typed adjacency proof, the certificate is revoked and moved to the negative archive. If the system allows an adjacency claim that changes under invariant stress tests, such as phi goes to phi plus c, lift shift by 2 pi integers, or cut relocation, the adjacency validator is revoked and repaired. If scale adjacency is accepted without a declared coarse-grain interface, that validator is revoked for scale smuggling. If transport adjacency is accepted without a declared transport mapping, that validator is revoked. If boundary adjacency is accepted without typed boundary evidence in D of W, that validator is revoked. Any future change to adjacency class rules must be versioned publicly. Hidden changes trigger revocation. Always, peace be upon you.